Hello, let us continue the discussion on first law of thermodynamics. In this session, let us work out some more examples to get the concepts clear. So let me look at this example. A system comprising of a gas of 5 kg mass undergoes expansion process from 1 megapascal and 0.5 meter cube to 0.5 megapascal. So let me explain this. Let us consider coordinate system. So let me mark the initial state. Let us say this value is P1. P1. It has a initial pressure of 1 megapascal and the corresponding volume of say V1, 0.5 meter cube. It undergoes an expansion process. So let me mark the state. Let me mark state 2. This is state 1. This is state 2. So this pressure is 0.5 megapascal. Can I know the pressure value to find the volume value? Let us call it as V2. Let us call this as P2. Now it expands from state 1 to state 2 like this. Let us see. This equation, this expansion follows the law PV to the power of 1.3 is equal to constant. That's what exactly. Expansion process is governed by PV to the power of 1.3 equal to constant. The internal energy of gas is given by U equal to 1.8 PV plus 85 kilojoule per kg. Here U is specific internal energy, P is pressure in kilopascal, V is specific volume in meter cube per kg. Determine heat and work interaction and change in internal energy. So is given mass is 5 kg. Mass of the system is 5 kg. Expansion follows the law PV to the power of 1.3 equal to constant. Work done. Look here. I have written M integral PdV. Is nothing but I have to find out the area under this curve. So it is displacement. Suppose you have a piston cylinder arrangement. Initial pressure is known, initial volume is known, then you can move the piston towards right, then final pressure to final volume. If you know, we can find out what is the work done. So integral PdV. Now here the expansion follows the law PV to the power of 1.3 equal to C, or in general I can write P V to the power of N equal to C. So let me replace this P by constant C by, so PV to the power, so it will become say V to the power of N. So here I can substitute, replace this P by C by V to the power of N and integrate between the limits 1 and 2. I'll be getting the equation like this. This m multiplied by small v will become capital V. So that's how we can find out this. Actually, in the chapter on thermodynamic processes, I'll derive this equation and I call this process as a polytropic process. So here it is required to solve this problem. That's the reason why I have brought in over here. But however, it is not a difficult thing. Only thing is you need to integrate this by replacing this P by C by V to the power of n. After integration, replace this thing by P1 V1 to the power of P1 V1 1.3 and P2 V2 1.3 and substitute, simplify, you will get this equation. Now, change in internal energy, that is U2 minus U1. If I put U2 here, this will become 1.8 P2 V2 plus 85. U1 here 1.8 P1 V1 plus 85. Then if I subtract one from the other, I will be getting this. Okay. If I multiply this with mass, then P2 capital V2, P1 capital V1 you get. Now the question is, the value of P1 is known, V1 is known, V2 is also, P2 is known, V2 is not known. We have to calculate V2. For that, what do we do is, P1 V1 to the power of 1.3 is equal to P2 V2 to the power of 1.3 we can write, because the expansion follows the law PV to the power of 1.3 equal to constant. So if I reorganize, I'll get V2 is equal to point and evaluate, substituting the values, I'll get V2 is equal to 0.852 meter cube. So go back, you know P2, now you know V2, you know P1, you know V1, substituting, you will be getting internal energy change. Same way, you go back to this equation, substitute those values, you will get the work done. For a system executing a process, closed system executing a process, delta Q is equal to delta U plus W. Delta U value you know, W value also you know, then I can find out delta Q value. So thus heat interaction is 113.5 kilojoule, work interaction is 246.7 kilojoule, and change in internal energy is minus 133.2 kilojoules. Okay, let us look at another example. A gas contained in a cylinder is compressed from 1 megapascal and 0.05 meter cube. That is, you consider this as P1, this you consider it as V1, to 2 megapascal, that is P2. Compression is governed by PV to the power of 1.4 equal to constant. Using this, we have to find out the final value. Internal energy follow this equation. So is similar to the previous problem. Determine heat, work and change in internal energy assuming compression process to be quasi-static. Also find out work interactions. That 180 kilojoule of heat is transferred to system between same state. Also explain why it is different from above. So now you know, as I explained earlier, P1 V1 to the power of 1.4 is equal to P2 V2 to the power of 1.4 we can write. Using that relationship, we can calculate V2 final. So, U1 means 7.5 P1 V1 minus 425. U2 is 7.5 P2 V2 minus 425. Subtract one from the other, you will get delta U is equal to this, and you also substitute the value of V2, you will get delta U. So, as I mentioned earlier, again work done. can be determined using this equation. Replace P as C by V to the power of n, and then you know P2, V2 and P1, V1. Substitute, you are going to get the work. And you know from first law, for a closed system executing a process, this is the equation. Substitute these values and you will be getting the value of heat. And the work value is known, internal change is also known. Now the question is, if 180 kilojoule of heat is transferred, then from first law again delta Q is equal to delta U plus W. Delta Q is 180 and delta U is 75 kilojoule. Then W, if you find out, it is 105 kilojoule. It is very different from this work. This is different from previous work because the process is not quasi-static in this case. Let us take another example. Determine the heat transfer and its direction for a system in which the perfect gas having a molecular weight of 16 is compressed from 101.3 kilopascal 20 degrees Celsius to a pressure of 600 kilopascals, following the law PV to the power of 1.3 equal to constant. Take specific heat at constant pressure of gas as 1.7 kilojoule per kg. Again, in subsequent chapter, we will be talking about ideal and real gases. There I will be dealing with. Anyway, you must have studied this in physics in your earlier classes. Let us say the specific gas constant R is given by universal gas constant divided by molecular weight of the gas. So earlier also I have mentioned the value of universal gas constant is 8.3143 into 10 to the power of 3 joule per kg. Okay? Molecular weight is 16. From here I will be getting specific gas constant. It's in joule, it's in kilojoule. So I know R value. You know Cp minus Cv is equal to R. That also you have studied in your physics class or chemistry class. So from here Cp value he has given, R value is known, I can always find out Cv value. And then gamma, the ratio of specific heats, we can find out 1.44. And as I said, P1 V1 to the power of 1.3 is equal to P2 V2 to the power of 1.3. From this equation, we can find V2. Same way, we can write for general gas equation T2 is equal to T1 P2 by P1 to the power of 1.3 minus 1.3 because P1 V1 by T1 is equal to P2 V2 by T2. From that relation, it is possible to find out this. So I can find out T2 value. Work done is equal to P1 V1 minus P2 V2 divided by N minus 1. Instead of that, P1 V1 I can replace by RT1 and P2 V2 I can replace by RT2, N value. So I'll get the work done. And a heat can also be determined by the polytropy process. I can calculate this equation again I derive subsequently in the thermodynamic processes chapter, right? So otherwise from the first law we can get this, there is no problem at all. So Q is equal to gamma minus N, gamma minus N to W. I can get gamma is nothing but 1.4, N is 1.3. Substitute those values and you will be able to get Q. You got W and Q. So such examples I just introduce. But here the problem is still I have not explained different thermodynamic processes like isobaric processes, isochoric process, polytropic process, adiabatic process, then isothermal process, then what is the work done And when the system executes such process, I have not explained, later we will be talking about in a thermodynamic process chapter. There I'll be deriving all these equations. You do not have to get bored out. Okay. It's the whole idea here is how we can calculate various thermodynamic interactions like work, heat, and then we can calculate the internal energy for a system executing a closed system executing a cycle and a closed system executing a process. Hope all these examples must have brought in clarity about the first law of thermodynamics as applied to a closed system and first law as applied to a closed system executing a cycle as well as executing a process. Thank you. Let us discuss first law as applied to open system in the next video.